Hello, I would first like to thank the Neville Center for the opportunity to make this presentation here today. I am going to speak about the justification of the proposed changes in the crack width calculation methods of both Eurocode 2 and Model Code 2020. This is a scheme of the presentation, so after a brief introduction, we will go through the proposed changes and their justification, and we will see then how they're implemented in the standards. And we will make a reference to whether we need to consider or not the effects of shrinkage, and then hopefully we will draw some conclusions. Okay, so first of all, I have to speak about the effect of cover, because this is, for some reason, still a very controversial issue. My experience is that there is a very, very significant effect, and these tests clearly show that. You can see that these two specimens have the same, virtually the same phi over rho effective ratio, but they have different covers. This specimen has a 32 millimeter cover, while this specimen has an 82 millimeter cover. And you can see that the behavior is very different. You can see that the mean crack spacing is only 13 centimeters for the lower cover, and almost 23 centimeters for the higher cover. So you can see that this effect is very important here. In terms of the crack width, measured crack width, you can see that for a very normal working stress of 250 MPa and a lower cover, so for the 32 millimeter cover, the crack width is about 0.3, which is what you would expect. But with the large cover, with the 82 millimeter cover, the crack spacing, the crack width, sorry, is over 0.6 millimeter, which is very high. The reason which I think explains this behavior is the fact that near the crack, near the bar, you have a lot of cracks forming, one on each rib. These are the very well-known go-to cracks. But very few of these cracks actually make it to the surface. And if you have a large cover, then a smaller number of these cracks make it to the surface. And this leads to a higher crack spacing at the surface when you have a larger cover. And this leads, of course, to a higher crack width. So let me go through the reasons why we even thought about changing the current European formulations. So the first reason is that these formulations are solely based on the behavior of a tie, and they do not acknowledge differences between the cracking behavior of bending and tension elements. The second reason is that the current definition of the effective area incurs in significant contradictions and results that are very, very strange, and it can also be simplified. The third reason is that the current models do not recognize the influence of casting position and cracking behavior, and I will show you some experimental evidence that this influence is actually quite significant. And so, by accounting for these effects, we will see that we obtain a significant improvement in agreement between the models and the experimental data. And finally, we will argue that the shrinkage effect can be disregarded, and the reasons for this will be explained. So in this figure, we are plotting the mean crack spacing against the phi over rho effective ratio. This is the same, would be the same for Eurocode or Model Code 2010. And you can see here that the coefficient of determination is not very high, The reason for this is because the phi over rho effective ratio does not explain all the variation. There is also the effect of cover. And you can also see that if we separate the bending test from the tension test, as is done here, you can see that the coefficient of determination for flexure is smaller than for tension. And we will come back to this figure later on. If we now plot the experimentally measured crack width against a crack width which is estimated on the basis of measured values, such as mean crack spacing and the tension in the reinforcement at the crack, and we multiply this by an estimated tension stiffening factor, you can see first of all that this evaluation is underestimating the actually measured crack width. The reason for this is most likely due to shrinkage, which occurs prior to the test and which is normally not reported in the databases, and which would lead to measuring not only the actual crack width, but also measuring in the release of the compression strain in the reinforcement due to the shrinkage occurring prior to the test. But the most important feature of this figure is the fact that the underestimation is much larger for flexural elements than for tension elements. And we will also come back to this difference later on, and we will see how we can correct this skew. If we look at the calibration of model code 2010, you can see that in terms of the crack spacing, it is fairly well calibrated. You have a correlation line which has a slope close to 1, and you have a high coefficient of determination, both for flexure and tension. If we look at the Eurocode 2, however, we are rather surprised, or maybe not. You can see that Eurocode 2 has a very, very strong overestimation of the crack spacing in tension tests. And this is due to factor K2, which we'll discuss later on. So moving on to the proposed changes. The first change has to do with the stress distribution between cracks prior to cracking. So Eurocode 2 already has this K2 factor, which is equal to 0.5 in bending and is equal to 1 in pure tension. So the reason behind this factor is very simple. If we look at an element subjected to tension, so a tie, and we look at what happens between the crack and the section where a new crack would form, so transfer length distant from the crack, we need this length because we have to transfer this force to the effective area of concrete through this bond forces along the reinforcement. So since the bond strength is limited, we need a certain length to achieve a new crack. If we look at the same phenomenon but for bending, well, we realize that the force we need to transfer through bond is smaller. If the full tension area is effective, it is actually 50% of what we need in tension. So we could get a new crack at a transfer length which would be half for flexure than what we have for tension. So this would be the basis of this K factor, which would be half in flexure than in tension according to Eurocode 2. But the reality is a little bit more complicated because not the whole tension area is not effective. If we have a very small element, yes, we could have the full tension area could be effective, but in general, this is not the case. If we have a very large element, the effective area could be very small with respect to the tension area, and in this situation, we would have a situation similar to what we have in a die. What is important here is what is the mean stress in the effective area, which is expressed by this equation. And if we simplify this and apply it to a rectangular cross-section, this KFL factor is just the height of the element minus the effective height divided by the height of the element. So for a small element where the HC effective is equal to h over 2, then the KFL would be equal to 0.5 as predicted by Eurocode 2. The second factor, which is very important, is the casting position. And we realized this effect when we tested by accident really a beam in flexure, which was virtually identical to another beam which we had tested in 2009. And we were a bit surprised when we compared the cracking patterns of the two specimens, because we could see that in the specimen tested here in 2009, we had a very wide cracks. We had only 14 cracks spaced almost 26 centimeters, whereas in the new test we did in 2017, we had 24 cracks, between 24 and 22 cracks, depending on the face we were looking at. And we had a crack spacing between 15 and 17 centimeters. So the behavior was extremely different. And we were puzzling over these results for quite a long time. And then we finally realized that when we tested these elements in 2009, these were cast in pour bond conditions. So the reinforcement was at the top when casting was performed. And these tests were cast on site. So the workmanship was not the same as in a laboratory. Whereas in the elements we tested in 2017, the reinforcement in this case was at the bottom when cast, and they were cast in the laboratory. So we realized that this could be a problem of casting position. We were able to confirm this effect when we tested these ties in tension. In these ties, we have two faces. One of them is which are actually the lateral faces, and one of them was cast in good bond conditions, while the other was cast in poor bond conditions. And by comparing the cracking pattern between the two side faces, we could confirm this effect very clearly. And this is just to show you the results. So you can see here for a 16 millimeter bar and 32 millimeter cover, you can see that in the face with good bond conditions, we have many more cracks than in the face with poor bond conditions. And the same happens when we look at the specimen with 25 millimeter bars, many more cracks where we have good bond conditions with respect to the number of cracks which you have in the face with poor bond conditions. This is just a summary of these results. And you can see with a 16 millimeter bar and a 32 millimeter cover, we have an increase in the crack spacing of almost 16% when we go from good to poor bond conditions. With a larger cover, 82 millimeters, we have an increase of only 5.4. And with the 25 millimeter bars, the proportions are an increase of 50% almost for a smaller cover, and for the larger cover we have up to 25%. This of course is a very well-known phenomenon, that when you concrete an element, you have settlement and you have bleeding. The water goes up, and what you get are water pockets below your reinforcement, so that the concrete is not in contact with, sorry, the bar is not in contact with concrete along the full perimeter, but has some voids at the lower part. We did not have enough experimental evidence to really make a very detailed proposal. So we decided to make a very rough, a very coarse proposal, which was to introduce a KB factor of 1.2 for elements cast in poor casting position, and a KB factor of 0.9 for elements cast in good position. We also carried out very recently in 2020 further tests to further investigate this casting position effect, and here are the results. So we are representing the crack spacing for poor bond conditions against the crack spacing for good bond conditions, and you can see that all of the points fall above the 45-degree line, which means that in all cases we had larger crack spacings when we had poor bond conditions. And another very interesting result here is that we separated the results between the specimens which were concreted on site and the specimens which were concreted in the laboratory. So on site they are the red symbols, and you can see that we have a larger effect when the workmanship is poor with respect with the effect we have in a laboratory. Okay, we decided also that we had to redefine the effective area, and this was because mainly of two arguments. The first one is that the current definition leads to unreasonable results, because if you have a concrete square like this, very large, and just a single bar in the middle, then with the current definition, the full concrete area around the bar is effective no matter how large the element, and this is just not reasonable. And the other reason was that the term which limits the effective height for flexural elements, this h minus x over 3, leads to very strange results when you apply it to practical cases. And this is just an example. For the ties, we had the full area of the section was effective, but for the elements in bending, according to the current definition of the effective area, we had a very small height which was effective, and this is because of this term, and this just does not seem reasonable. So we redefine the effective area. Basically what we are saying is that the total height cannot be larger than 3.5 times the mechanical cover plus the spacing between bars. And we also say that the effective area is limited to a distance of 5 diameters from the bar. So this, you have here the new definition. We don't have to look for h minus x over 3. We do have to limit it, of course, to the tension area. This is how the definition of the effective area looks for the new proposal. So if we had only this with the old proposal, with the current proposal, let's say, with the new proposal, we have something which is much more reasonable, much more similar to what we have in tension for the flexural tests. Okay, if we go back to this figure, which I showed before, which is the mean crack spacing versus the phi over rho effective ratio, but in this case, we include the correction regarding KFL for the stress distribution between cracks. You can see that what happens is that for flexure, we get a much better coefficient of determination. This was 0.4 before. It goes up to 0.5 for flexure, while for tension, it basically stays the same because we have not made any changes. KFL is still 1 for tension elements. Then we have the influence of curvature. So for curvature, in this figure, we are showing two tests. One of them has a cover with round symbols, has a cover of 32 millimeters, and the other with the square symbols has a cover of 82 millimeters. And the black symbols represent the measured crack width at the level of the reinforcement, whereas the white symbols represent the measured crack width at the most tension fiber. And the gray symbols are obtained by multiplying the value of the black symbols by this correction factor. And you can see that the gray symbols fall almost on top of the white symbols, which proves that this correction is actually a very, very good one. Okay, so the proposed model looks something like this. You have calibration factors, Kc and K phi over rho effective. Kc would be equal to 1.5, and K phi over rho effective would be equal to 1 over 7.2. This is actually the same number which you obtain from bond theory, and this can be done because we have a KB factor of 0.9 for good bond conditions. This is the reason for why this factor is not 1 for good bond conditions. It's just an aesthetical feature. So we have introduced KFL and KB. These are the novelties, let's say, apart from the new calibration. And then for the strain of steel with respect to concrete, we have the traditional expression, but it is multiplied by the K curvature factor, which we just saw is very necessary. This factor is actually fundamental to obtain good results when you have large bars and large covers. The crack width, the design crack width, is formulated as the mean crack width multiplied by a factor which is equal to 1.7. I think making this factor explicit as we are doing here is important, because the fact that we had this factor implicit in earlier codes led to a lot of confusion, especially among researchers. Now, if we go back to this other graph, which was the measured crack width with respect to the estimated crack width, where the only difference here is that we have introduced the K curvature factor. You can see that by introducing this K curvature factor, this Q which we had before is corrected. Now the flexure and the tension have almost the same regression lines. So this is a very strong argument of the need to introduce this K curvature factor. This is the calibration of the Model Code 2020 and also the Eurocode 2 proposal for crack spacing. And you can see that, well, you have a correlation slope close to 1, and you have higher actually determination factors than what we saw before. So we do get better agreement. And of course, we get much better agreement with respect to tension results as they are currently modeled by Eurocode 2. If we look at statistics, you can see here the statistics for flexion and tension for Model Code 2010, Eurocode 2, the current version, as well as for the new proposal. And you can see that in terms of the mean square error, we go from 38 or 35 to 29 for flexion, from 38 to an 83 to 31 in tension. And in terms of the coefficient of variation, we also have a smaller coefficient of variation for flexure and much smaller. Unfortunately, you cannot see it because of my camera, but for tension, this coefficient of variation is 15.6, so much lower than the ones provided by Model Code and Eurocode. We also tested this calibration against an independent data set. This was provided after calibration by Gintaris Kaklauskas, and here is a list of the tests which are included in this database. And this is the plot of the agreement between the theoretical and experimental values of crack spacing. And these are the statistics. So you can see that the mean square error goes from 27 or 26 to 23.5, and the coefficient of variation goes from 23 or 24 to 18.9 for the independent set of tests. These tests only include flexural tests, so we do not have the comparison for tension. Okay, regarding the effects of shrinkage, well, if we go to the classical analysis, let's say, and we have a tie here subjected to an actual force, and we look what is happening at the crack. Well, at the crack, the stress in steel is due to the force, and the strain of steel is due to the force, and the strain of concrete is due only to the shrinkage strain. So the difference between these two values is the difference due to the force plus the difference due to shrinkage. So we would have to add in the strain term the shrinkage strain. If we look at what happens between cracks and we make a mean value, in the end, what we obtain is that to the classical formulation, we would have to add the shrinkage strains times 1 minus the tension stiffening factor. So according to this, there would be an effect of shrinkage. However, there are two favorable effects which reduce the effect of shrinkage. One of them is that in the crack formation phase, the element will be subjected to the cracking force, and shrinkage will induce tensile stresses in concrete, which would reduce the cracking force, so that the restraining force would become smaller with time, and this would reduce the steel strain. And then there's another effect regarding the stabilized cracking phase, which is that the development of shrinkage will also lead to increased stresses between cracks, which would actually reduce the transfer length. And therefore you have two cracks which are spaced 2 times the transfer length. Due to the effect of shrinkage, you get a new crack in between. So for the first effect, we made a small calculation where we applied step-by-step analysis, to see how the cracking force would evolve through time and obtain from that calculation the crack width. We studied 4 sections which have a very different height and which have very different reinforcement ratios. So you can say they cover pretty much most of the practical field. And if we look at the results, we can see here the cracking force as a function of time. And you can see that the cracking force is increasing at first, and this is due to the increase in the tensile strength with time. But after a while, due to the development of stresses from shrinkage, the cracking force decreases. So if we look at what would be the crack width along time, you can see that this crack width would be increasing. And if we do the calculation ignoring shrinkage, yes, we are actually underestimating a little bit the crack width. But this underestimation goes from 9 to 18%. So it is not really very dramatic. And since we have many other uncertainties when dealing with cracking, we felt it was acceptable to ignore this effect and disregard cracking for the crack formation stage. If we look at the stabilized cracking stage, you have here the linear analysis applying the aging coefficient method. So the element would shorten this much. This would be the shortening strain. You would have reduction of the tensile stresses in the steel, and you have an increase in the tensile stresses in concrete. So if we try to determine what is the transfer length by classical analysis, first through equilibrium of the bar, you would get the difference between the stress at the crack and the stress at the end of the transfer length through this this expression. Actually, this is the expression of the transfer length as a function of this difference of stresses. And if we then look at the equilibrium between sections, between the section of the crack and the section where the new crack will form, here, what we have here is that the maximum stress we can have here when we form a new crack would be the strength of the tensile strength of concrete times the effective area minus the force generated by the shrinkage strain. So if we can obtain this difference of stresses, which affects intervenes in the expression of the transfer length from this equilibrium, and in the end we can see that the transfer length, which was equal to this expression as shown before, we get the regular expression of the transfer length, but then we have a factor which is here, which you cannot see unfortunately due to my screen, which is the effect of shrinkage. And the effect of shrinkage is actually shortening the transfer length. So if we have two cracks which are formed 2 transfer lengths apart, which is the maximum that you can have, then due to shrinkage you would get a new crack in between, and this new crack will of course reduce to half the crack width, and therefore you would have a much very favorable effect. Okay, So if we go to the conclusions, the first is that we have introduced a new coefficient um, to account for the effects of non-uniform stress distribution, KFL. The introduction of this factor increases the correlation between the measured and predicted crack spacing and allows to delete the h minus x over 3 limit to the effective height currently implemented in Model Code 2010 as well as in Eurocode 2. Recent experimental data also demonstrates that casting position has a very strong influence on crack spacing, increasing it when the tension bars are concreted in poor casting position. And this has been accounting very coarsely by a factor KB. Hopefully this factor can be refined in the future when more experimental data is available, but it is very clear that not only the casting position is important, it is also the workmanship is very, very important. We have proposed a new definition of the effective area to eliminate some of the inconsistencies of the current model. And this, together with factor KFL, allows to increase the correlation between the measured crack spacing and the bond term of the crack spacing equation. And this is so particularly in flexure. Accounting for the above consideration, we have had to recalibrate the model so that we obtain results that are similar to what we had before, because we're looking at the same experimental base. And this recalibration results in significantly improved statistical performance in terms of the mean squared error, and also in terms of the coefficient of variation. Regarding the effects of shrinkage, we can say that in the crack formation phase, the crack width is underestimated by a small amount due to the reduction of the cracking force. And it seems reasonable not to consider it because it improves ease of use, plus it has low consequences. And for the stabilized cracking phase, a new crack would form between the two most spaced cracks because the development of shrinkage would lead to a reduction in the transfer length. This would offset, in most cases, the increase of the crack width due to shrinkage. Okay, so thank you very much, and I am open to your questions.